Defining kernels, it is also possible to define application-specific kernels. Kernels are generally considered to be measures of similarity in the sense that k of xy takes a larger value as x and y are more similar from the point of view of the application. This implies that any prior knowledge we have regarding the application can be provided to the learner through appropriately defined kernels. Kernel engineering and such use of kernels can be seen as another example of a hint. This is from section 11.4.8.4. There are string kernels, tree kernels, graph kernels, and so on. Vert, Kazuda, and Strongkops. In 2004, depending on how we represent the data and how we measure similarity in that representation. For example, given two documents, the number of words appearing in both may be a kernel. Let us say D1 and D2 are two documents, and an impossible representation is called a bag of words, is where we predefine m words relevant for the application, and we define phi of D1 as the m-dimensional binary vector whose dimensions phi of D2 counts the number of shared words. Here we see that if we directly define the implement k of D1, D2 as the number of shared words, we do not need to pre-select m words and can use just any word in the vocabulary, of course, after discarding uninformative words like of and etc. And we will not need to generate the bag of words as representation explicitly, and it would be as if we allowed m to be as large as we want. Sometimes, for example, in bioinformatics applications, we can calculate a similarity score between two objects, which may not necessarily be positive semi-definite. Given two streams of genes, the kernel measures the added distance, namely how many operations, insertions, deletions, substitutions it takes to convert one stream into another. This is also called alignment. In such a case, the trick is to define a set of m templates and represent an object as the m-dimensional vector of scores to all the templates. That is, if mi, I starting from 1 to capital M are the templates, and s of x to the t mi is the score between x to the t and mi, then we define that phi of x to the t is equals to the transpose of the vector s of x to the t m1, s of x to the t m2, and so on until s of x to the t mm, where this index m is capital M. And we define the empirical kernel map as k of x to the t x to the s equals to phi of x to the t to the transpose times phi of x to the s, which is a valid kernel. Sometimes we have a binary score function. For example, two proteins may interact or not, and we want to be able to generalize from this to scores to binary instances, to arbitrary instances. In such a case, the trick is to define a graph where the nodes are the instances and the two nodes are linked if they interact, that is, if the binary score returns 1. Then we say that the two nodes that are not immediately linked are similar if the path between them is short or if they are connected by many paths. This converts pairwise local interactions to a global similarity measure, rather like defining a geodesic distance, used in an isomap, section 6.7, and it is called the diffusion kernel. If p of x is a probability density, then k of x to the tx is equal to p of x to the t times p of x, and is a valid kernel. Such a multiplication is of two probability densities with two different input parameters. This is used when p of x is a generative model for x, measuring how likely it is that we see x. For example, if x is a sequence, p of x can be a hidden Markov model. In chapter 15, we will see more detailed. With this kernel, k of x to the tx will take a high value if both x to the t and x are likely to have been generated by the same model. It is also possible to parameterize the generative model as p of x conditioning on theta and learn theta from data. This is called the feature kernel. It's proposed by Dracola and Hostler in 1998.